Hi all. In this video, we are going to learn another very interesting method of supervised learning, which is called decision trees. So this in some sense represents the way in which we human beings also take decisions. Maybe that's why it's called decision tree. So essentially, it represents a hierarchical decision making process. What do I mean by the term hierarchical? This is the key term that differentiates decision trees from logistic regression or support vector machines. So as we saw in the previous examples of supervised learning algorithms, that you can have several different features using which you do binary classification or even multiple multi-class classification. So now SVM and logistic regression can be used to extract information about which feature is more important, which feature is less important. But the crucial difference with decision trees is that in this case, the hierarchy is the driving factor in the algorithm design. What do I mean? Let's take a simple example. Suppose one night you are feeling very hungry and you don't really want to cook food. So now you have two options. Either you want to go out, or you could order food online. And now you need to decide which of these two options you want to opt for. So there can be many different factors which can influence this decision making process, but for the sake of simplicity, let's just talk of two factors, which is temperature and rain. So let's say that the first factor that you consider is the temperature. So now let's say there are three options. The temperature could be very, very hot. The temperature could be very, very cold, or the temperature could be nice. So now if the temperature is hot, perhaps you decide that you will order food. You won't go out. If the temperature is also very cold, then again you will order food. But if the temperature is nice, then you could go out. What else does it depend on? Then the next thing you will check is whether it is raining or not. And again, there are, let's say, two options. The first option is, let's say, there is a downpour, and the other option is that there is a slight drizzle or it is dry. And now you may say, if it is a downpour, you will again order, and if it is dry, then you will go out. So this is essentially the thought process behind decision tree algorithm, that given a set of features and a set of classes, you would want to design a hierarchical structure of this kind, which helps you in categorizing your given input data point. So these are called the nodes of your tree. So this temperature and rain are the nodes of your tree and represent the attributes or features which are used to do your classification. And these are called the values of a given attribute. So in this case, the attribute temperature has three possible values: cold, nice, and hot. And the attribute rain has two values: one is downpour and one is drizzle. So this is the main thought process behind decision tree algorithms. And as you can see, obviously, that one clear advantage of decision trees is that they can handle this kind of symbolic attributes and values. In the case of SVM and logistic regression, the values of attributes needed to be numbers, because that is what SVM and logistic regression is designed to optimize on. But for the case of decision trees, you do not need numbers and you could work with symbolic attributes and values. So now the next question that arises is that, let's say we are given this data set, which I have taken from the book Machine Learning by Tom Michel. So this data set represents whether you will want to play tennis or not, and as you can see the options are no, yes, and so on. And it depends on four different attributes. You have an outlook which can be sunny, overcast, or rain. You can have temperature which can be hot, mild, or cool. You can have humidity which can be high or normal, and you can have wind which can be weak or strong. Now, using these four attributes, you need to predict whether on a given day you will want to play tennis or not. So now the obvious question is that if we want to solve it using decision trees, which of these four attributes should be our root node? So what's a root node? In this case, our decision tree started with this attribute of temperature. So the first attribute or feature in the decision tree at the top is what is called the root node. So now we obviously need a mathematical formulation to figure out that which of these attributes you want to place at the top. And once you have decided that, you want to then figure out which is next, which is next, which is next, and so on. So there are, as it turns out, many different ways of doing this. But one of the most important ways of doing this is by using what is called entropy. So as you might have studied in previous courses in your college, that entropy is essentially a measure of the disorder of a given random variable. And so if your outlook has high entropy, and so if your attribute has high entropy, it means that it has high disorder, which means that its predicting power is actually very low. So such an attribute will not be placed as a root node. So the attribute that we place as the root node is the one which has the lowest entropy, which means it has the lowest disorder, which means it has high predicting power. So let's see with the help of an example what exactly are we talking about. So here what I've done is that I have taken that data set and I have computed the corresponding output values for each value of each attribute. So in this table you have outlook which can be sunny, overcast, or rain. So now I only look at the values sunny for outlook and see for how many of them correspondingly you have no or yes. So let's say we have sunny which comes here, 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 and here. So there are 5 times that the attribute outlook takes the value sunny. And for sunny, here we have no, here we have no, then here again we have no, then we have a yes, and then again we have a yes. What that means is that corresponding to the attribute outlook value sunny, you have 2 yes and 3 no. Similarly, for the outlook overcast, you will have 4 yes and 0 no's. For outlook rain, you will have 3 yes and 2 no, and so on for other attribute values. This I strongly recommend that you check to make sure that this is indeed correctly reflecting your given data set. Then in order to compute the entropy, you have to convert these numbers into corresponding probabilities. So now your P1 is just this value divided by the sum of yes and no. So in this case, it becomes 2 divided by 5, which is 0.4. Similarly, P2 is 3 divided by 5, which is 0.6. Similarly, 4 by 4 is 1, 0 by 4 is 0. 3 by 5 is 0.6, 2 by 5 is 0.4, and so on. Now, what is entropy? Entropy, as we know, is given by minus summation I pi log pi. So this was discovered by both Boltzmann as well as Shannon in statistical mechanics and communication theory respectively, and is a very widely used formula in many applications in science and engineering. So now in this case we have I equal to 1 and 2. So this HV that you see over here is minus 0.4 log 0.4 and minus 0.6 log 0.6. So now in this case, we generally use logarithm to the base 2, and that's how you will get this particular value of 0.971. Similarly, here you will get 0 because minus 1 log 1 is 0 and minus 0 log 0 is also 0. So, and 3 and 2 will give 0.6 and 0.4, from where you again get 0.971. Now look at this. When the outlook is overcast, all the options are yes, meaning then in this case, you do not need to bother about any other attribute. And here the entropy is exactly 0. So this is a low entropy case because your outcome is having low disorder, meaning you have high order, which means that if you know that the outlook is overcast, you can exactly predict what your final outcome will be. So this is what your entropy method selects for, that the attributes which have a lower value of entropy are given higher importance. So now how do you compute the overall entropy for the attribute? So now what you have to do is that using these entropy values, you have to compute the normalized entropy. Normalization with respect to what? With respect to the number of times a particular attribute value appears in your data set. So this 0.347 is obtained by 0.971 multiplied by 5, which is a sum of 2 and 3, divided by 14. What is 14? 14 is the number of rows in your data set. That's how you normalize this. So this 0.971 into 5 by 14 is this. 0 into 4 by 14 is again 0. 0.971 into 5 by 14 is 0.347. And when you add all these three numbers, you get the overall entropy for that particular feature or attribute. Similarly, for temperature, you find the individual entropies, then the normalized entropies. So for example, this 0.286 is 1 into 4 by 14. 0.394 is 0.918 into 6 by 14, and so on. So now what you do is that out of these overall entropy values, you pick the attribute which has the lowest entropy, because low entropy means low disorder, which means better predictive power. So outlook attribute has more predictive power than any of these three other attributes or features. Now instead of using entropy, sometimes it is mentioned that you use this quantity called information gain. So information gain is nothing but the overall entropy minus the attribute entropy. So if you are minimizing the entropy, you have to maximize the information gain. These two say the same story, so there is no fundamental difference between entropy and information gain. It is just a different way of representing the same thing. And what is this overall entropy? Overall entropy is nothing but just the entropy of the entire data set. So in the entire data set, you have yes 9 times and you have no 5 times. So correspondingly, you have P1 and P2, and then you find your entropy value from here. So this is what your decision tree algorithm is mainly doing, that you figure out your entropy values, find the normalized entropy, then find the overall attribute entropy, and then take the one which has the lowest attribute or feature entropy, or the one which has the highest information gain. So what that means is that if we now want to draw a decision tree for this data set, we will place outlook at our root, and it will have 3 possibilities. The first possibility is sunny, then you have overcast, and then you have rain. If you have an overcast, then as we just saw that if it's an overcast, then the output is definitely going to be yes, because in the overcast case, no is totally 0. So now here we have the output of yes. Now because we have reached an output of yes, we do not need to further bifurcate over here. So this node has ended over here. But sunny and rain have to still propagate because these are not completely decisive. So now we need to figure out that if the outlook is rain, then what should be our next node over here. So for that, what we do is that we go back to our data set and then we select the rows for which the outlook is rain. So we select the 4th, 5th, 6th, 10th and 14th row. And now we carry out the same analysis as what we did earlier. So now this table represents the subset of your initial data set for which the attribute value of outlook is rain. And then we do the same process. We find the entropy, normalized entropy, overall feature entropy, and then we select the one which has the minimum entropy or the maximum information gain. And if you do that, you find that if your outlook is rain, then the next node has to be wind. So you do that. So you draw your next attribute or feature value over here, which is wind. And now what you will find is that there are two options. One is your wind is strong and one is your wind is weak. And if your wind is strong, that leads to the answer of no. If the wind is weak, the answer is yes. Similarly, you can do the same process if the outlook is sunny, and then what you will find is that your next attribute value is humidity, which can take two possible values. One is your humidity is high and then your humidity is normal. So if your humidity is high, you again say no to tennis, but if your humidity is normal, you say yes to tennis. So now since our final nodes are only yes and no, we have reached our endpoint for our decision tree. One thing that you notice that our initial data set had 4 different attributes: outlook, temperature, humidity and wind. But in the final decision tree that we draw, temperature does not play any role whatsoever because it is not required to do our classification. So now let's write the formalism a little bit more formally. So let's say you have a data set which has many attributes which are represented by A. So this is one of the attributes of your data set. S is the total collection of examples in your data set. Let's say SAV represents the subset of S for which attribute A has value V, and let's say your HS represents the entropy of the entire data set S. HASV represents the entropy of your subset SAV, and your HA represents entropy of your attribute A. So what you do is that you first find the entropy corresponding to each attribute value. That's what we did in that table. This is minus Pi log Pi. Then after doing that, you find the normalized entropy, which we can denote by HA, which is summation over all the values belonging to the attribute A into the cardinality of the set SAV divided by the cardinality of the set S multiplied by H of SAV, and this will give you the entropy. So you can choose the attribute which has the minimum HA, or you can choose the attribute which has the maximum information gain, which is defined as HS minus HA. And as I just said, this quantity is called the information gain. And of course, the logarithm that you take has to have a base of 2. So this is the basic algorithm that we follow, that for a given data set you compute the entropy and choose the attribute which has a minimum entropy, and then you go on in that manner, or you choose the node which has a maximum information gain. These two will give the exact same answer, doesn't really make a difference, and then you create your decision tree in that order. So this particular algorithm of creating decision trees is what is called the ID3 algorithm. There are several different algorithms that one can use, but this ID3 has been found to have several advantages and is commonly used in many decision tree applications. ID3 stands for iterative dichotomizer 3. Now this information gain or entropy method is very intuitive and easy to understand. But one problem with this method is that this computation of logarithm is somewhat expensive. If you have a small data set, it doesn't really matter. But if you have a large data set which have lots of features, lots of different outcomes, then computing logarithms many times will slow down your classification process. So in order to speed up your calculation process, what you do is you use this thing called the Gini index, or what is also called the Gini impurity. And the Gini impurity is given by 1 minus summation pi square. So everything else remains the same, but what changes in the Gini index is that instead of calculating entropy, what you calculate is the Gini impurity, which is given by this formula. So here you have P1 and P2, which are same as the table you saw earlier, but now this G is the Gini impurity, which means it is 1 minus 0.4 square minus 0.6 square, which gives 0.480. Then again you normalize this in the exact same way as what we did earlier for the information gain or the entropy method, and then you find the final attribute Gini index for each attribute, and you pick the one which has the minimum Gini entropy. So this works almost in the same manner as information gain. It will give you the almost same results, but it will be much faster to implement as compared to the information gain method. So now decision trees have several different advantages. As I said, you can also handle symbolic attributes and values using this method, which was not possible in SVM or logistic regression. But the nice thing is that your decision trees can also handle numeric values. So what would you do in that case if your attributes had numerical values? In that case, you have to then do these different options using different ranges of the attribute value. So let's say your attribute could be, let's say, between 0 to 10. You could say, okay, I will take 0 to 5 as one possible set and 6 to 10 as another possible set. So you will have to bifurcate your given input values in various ranges and then do the computations in the same way for those ranges and thereby form your decision tree. Now, although this process is very nice and very useful, this suffers from a serious problem of overfitting, because it sort of takes care of every single attribute and every single value that is given. It tends to find decision trees which are overly representing the given training data set. So there are many ways of taking care of overfitting in decision trees, but the two most important methods are called pre-pruning and post-pruning. So pruning means cutting down the decision tree. Like when you have some actual physical real tree in your house, it tends to grow in a wild manner. So, in order to give it a shape, in order to make it beautiful, you do pruning from time to time. Even if you don't do, but either somebody in your family or maybe you have a gardener who does this pruning of the trees from time to time. In decision trees also, we adopt a similar process. So the first method is what is called pre-pruning, which means that you do the pruning while you are building the decision tree. So this is while building the decision tree, you do this pre-pruning based on some significance threshold, which means you can say that if your entropy value of a node becomes very high after a point, then you will kind of just ignore those nodes and you will stop your decision tree at some point. But the problem with pre-pruning is that it is very hard to objectively figure out what that threshold should be. So what is more commonly used in practice is what is called post-pruning, and which is done based on a validation set. So what you do is that you first train your decision tree using the training data set. You do not do any pre-pruning, and then once you have your decision tree which is ready, you then remove some nodes and see how its accuracy changes on a given validation data set. And then you do this trial and error multiple times, and then you figure out what would be the pruned decision tree which would give the best accuracy on your validation data set. Now again, your validation data set or even your training data set could also have some missing values, and in that case you could assign a value which is the most common for that particular attribute, or use some other probability measure to determine the missing values of a given attribute. So now your decision trees of course are very useful, but like any method, they have some advantages as well as some disadvantages. So let's try to understand first what are the advantages of the decision tree algorithm. So the first advantage is that they are easy to interpret. As you just saw, in the example that we had, for this decision tree, it is very easy to interpret about if you are getting an answer of no, then why is it that you're getting no? It is because the outlook was rain and the wind was strong. If you're getting, let's say, yes over here, then you know it is exactly because the outlook was sunny and the humidity was normal. So there is absolutely zero ambiguity in your prediction, and that is very important because otherwise many other machine learning algorithms could essentially be functioning like a black box. The second very important advantage is that it is easy to mix data types. As I just said, that decision trees can also handle symbolic attribute values. The example that we saw in this video was itself using symbolic attribute values. So in decision trees, unlike your SVM and logistic regression, you could have a problem where you have both symbolic values as well as numerical values, and decision trees can handle them very easily. Although it is also possible to do this using SVM or logistic regression, but it is not very natural in that case. The third advantage is that it is very robust to outliers. And this is again because, like in the SVM case, we are not doing any probability estimate. So for example, if you get an output of yes or no for a binary classification process, then we are not able to say in the decision tree algorithm whether your output is yes with a probability of 75% or 85%. We are just able to say that the output is yes or no. So that gives you an advantage that you are able to handle outliers, but of course that gives you also a disadvantage that you are no longer able to make probability estimates like you did in logistic regression. So there is always a give and take that you have to accept in any machine learning algorithm. And the final important point is that it scales well to large data sets. And this is because all that you are doing are computing some entropy or the Gini index values, which are relatively very easy to compute, unlike logistic regression where you have to do a gradient descent, and that's a complicated optimization process. But here no such gradient descent or optimization or Lagrange multiplier methods are required. Here you just compute the entropy or the Gini index and do a sorting of those values and then choose the ones which are minimum or maximum depending on which method you are using. That's why decision tree algorithms, they scale very well to large data sets. So these are some of the advantages of decision tree algorithms. Now let's see what are some of the disadvantages. As I just mentioned that a decision tree is prone to overfitting. So that of course is the first and most important disadvantage that we have, and that can be handled using pre-pruning or post-pruning and some other methods that we are going to discuss in the next video. But nevertheless, this is a serious problem with decision tree. The other more serious problem perhaps is that decision trees are inherently unstable due to their hierarchical nature. What that means is that if I make even small changes in your input data set, then it is possible that the decision tree structure undergoes a major change, because if because of a small change, one of the attributes now has a lower entropy compared to the other attribute, it can now become the root node, thereby completely changing the nodes which follow below it. And that's why this is a very, very unstable method. Now, to address these problems, overfitting and lack of stability at one stroke, people have introduced a method which is called random forest. So in random forest, what you do is that instead of building just one tree, you build many different decision trees and take an average over all of them. So this does make the process slower, but it helps you in taking care of overfitting and instability of your decision tree hierarchical structure. So I hope you found this decision tree algorithm interesting. In the next video, we will be talking about random forests, and we will also compare random forest with SVM as well as logistic regression. So till then, stay connected.